Hi, my name is Murtaza Nader and welcome to Physics 2211 Lab 5 Falling Slinky. The main goal of this lab is to forecast the motion of a falling slinky and assess how its environment influences that motion. I'll be using the tracker software to capture the actual movement and Glow script to build a computational model for predicting and visualizing the ideal motion. The primary aim here is to check if the bottom of the slinky remains unmoved in the computational model and see how that compares to the data from tracker. A brief preview of the main results of the lab is that despite slight variations between the real-life observations and the simulated predictions, the bottom of the slinky largely stays in a fixed position throughout its descent. It's also important to state that the system in this lab is the slinky while the surroundings is the Earth and everything else. In this lab, we're utilizing several key physics principles to analyze the motion of the slinky. First step is Newton's second law, which is also known as the momentum principle. This principle tells us that the change in momentum of a system is directly proportional to the net force applied. By using this law, we can drive equations that help us update both the velocity and position of the slinky over time as it falls. Next, we consider the drag force, which represents the resistance an object experiences when it moves through a medium like air. The drag force is dependent on factors such as the speed of the object and a proportionality constant that varies with shape and surface characteristics. This force opposes the motion and can significantly affect the slinky's falling speed. Finally, we take into account the gravitational force and the slinky's tension force. The gravitational force acts downward, calculated as mass times the acceleration due to gravity. On the other hand, the tension within the slinky exerts an upward force, balancing out gravity to some extent. These forces together determine the behavior of the slinky, especially in understanding whether the bottom part remains stationary or not during its descent. To analyze the object, we will be using this video which was provided for us. For calibration, we know that the Slinky has a mass of 218 grams or 0.218 kg, and we're using Derek's height, which is 1.75 meters, as a scale reference. The Slinky starts from rest, so its initial velocity is zero, and we measure its position from the moment it's released. This setup provides us with the necessary data to track and analyze the Slinky's motion accurately. Next, we'll move on to creating the code for our computational model. The first step is to set up all the initial conditions, most of which we obtained from our track analysis. These include values like the slinky's mass, its initial position, initial velocity, and the drag proportionally constant. This constant is crucial for our drag force equation to accurately reflect real-world conditions, and it was determined through a process of trial and error to best fit the observed data. Computational model is divided into two main sections. The first section, or the first while loop, focuses on the time period when the bottom of the slinky remains stationary. During this phase, we aim to analyze the behavior of the bottom segment of the slinky by applying the velocity and position update formulas. To use these formulas, we need to consider the net force acting on the slinky. Since the bottom part is not moving, the net force must be zero. The Earth exerts a downward gravitational force on the slinky, but since the bottom remains stationary, there must be an equal and opposite force, the tension force, counteracting gravity. This balance of forces keeps the bottom of the slinky in place during the initial period. Now here's the second while loop. In the computational model, during the first while loop, we expect the slinky's position to remain constant because the net force acting on it is zero. This keeps the bottom stationary. However, once the top part of the slinky reaches the bottom and the entire slinky starts to fall, it is no longer stationary and the net force is no longer zero. In addition to the gravitational force pulling it downward, there is also a drag force that becomes significant. This drag force is proportional to the square of the slinky's velocity. To model this motion, we will continue using the velocity and position update formulas to track the slinky's changing position over time as it falls under the influence of both gravity and air resistance. Here are the results, and we have a graph comparing the observed versus predicted positions of the bottom of the slinky. The blue line represents our computational model, while the orange dots show the actual data tracked using the tracker software. As you can see, the model closely aligns with the real-world observations, especially when the bottom of the slinky remains stationary. However, there are some fluctuations, particularly when the slinky begins to fall. Possible source of error for this lab is firstly external influences like air currents or slight vibrations could have affected the slinky's motion, which our model does not account for. Another factor is human error in using the tracker software and manually placing the center of mass. Also, while we used the drag force constant to stimulate air resistance, this value was adjusted through trial and error. The simplification might not fully capture the real-world drag acting on the slinky, leading to small deviations in our predictions. For this lab, we did not have a what if and what does it mean question already given to us, so I made two of mine. The first one is what if we attached a larger weight to the bottom of the slinky? If we had done that, the weight will stay stationary as long as the slinky is either long enough or has a large enough spring constant to balance the downward gravitational force with an equal and opposite tension force. If not, the weight will cause the slinky to move. And the second question, what does it mean when the bottom of the slinky stays stationary? It indicates that the forces in the vertical direction are perfectly balanced, and the downward pull of gravity is exactly cancelled out by the upward tension from the slinky, keeping it in place until the top reaches the bottom. Thank you very much for your attention, and I hope you learned something from our last lab here in Physics 2211.